Welcome to the webinar. We're talking about computer vision, bridging the gap between digital intelligence and the physical world. We are really fortunate to have our co-founder and CTO, Dr. Cody Phillips, with us. Cody has a PhD in computer vision machine learning from Penn. He was previously the co-founder and head of data science and algorithms at Avere. They were a construction-based computer vision company, which I'm sure he'll tell us a little bit about, that got acquired post-Series B. He has multiple patents in autonomous robotic vision systems, over 10 years of published academic research, and experience both here at Meridian as well as his former company of Avere, at Penn with the GRASP Laboratory for General Robotics Automation, Sensing, and Perception, uh, awarded multiple NSF grants, worked with DARPA and Army research labs, and much, much more. The smartest guy I know. So I'm going to let Cody take it from here.
Awesome. Thank you very much, Josh. So I wanted to start today with the question of what is computer vision? At the highest level, it means enabling computers to interpret and understand the visual world. Now, it is often confused with artificial intelligence, so I wanted to discuss the intersection of the two. So seeing at this graph, we have that artificial intelligence is on a high level, the having a artificial agent to do a task. Now, this does not necessarily require learning or machine learning, which is the next little sphere of this graph. For example, computers have been playing chess since the 1950s, and they've been doing so by searching and scoring moves until it found the best one. So if you can look, they call that the horizon, the chess horizon. If you can see far enough on the horizon, you can probably see the move that will beat the human player. That requires no learning. Now, as we demand more from these agents, learning is actually required. So a common task nowadays that demonstrates this is sentiment analysis. Say we want to automatically determine if a customer was unhappy or happy from a interaction with a customer care agent. Now, a simple rules-based agent, we might be able to say, look, if there contains an expletive, the user is probably unhappy. Now, if they have lots of happy words, like great, maybe they were happy. Now, without learning, we can see where that might fail. A very happy user might use an expletive, and that would break the simple model. To be a little bit more sophisticated, we would use machine learning. Now, for machine learning to work, we would have a bunch of positive responses that we know from the user, like this user had a great experience, they're happy, and a bunch of negative ones where we would say this user was upset. And what we would do is we would do some basic, maybe word frequencies. So if it has an expletive, sure, that could be some evidence towards upset, but it doesn't necessarily mean it. We would look more holistically at everything. And the role of the machine learning would be trying to say, based on all the statistics, this seems a little bit more happy than sad or upset. And based on which way it was leaning, we would say happy or upset. Now, that still sort of assumes we did some base statistics, like we did frequency analysis. Deeper still is deep learning, where I won't go into the techniques of that, but the computer from all of these examples learns not just some base statistics, but at its core defines this happy, upset space of all possible responses, and it kind of can feel where in that space these responses are. So that's called deep learning. Now, computer vision has analogs across this path, but at its core, computer vision is just enabling computers to interpret and understand the visual world. And at the lowest level, that's just problems of mathematics, physics, and geometry. So we might ask, for example, a very simple computer vision question is, what is the depth of my hand? Meaning, how far is my hand from the camera? Now, there's physics of the light forming the image. There's the math gradients, the boundaries of my hand contours. And then there's the geometry of triangulating the hand from two images. Let's say we have another image here, just like we have two eyes. From that, we should be able to figure out how far my hand is. Now, as where machine learning and artificial intelligence come in, is we can mix this geometry, the it's literally triangulation, with machine learning and specifically deep learning to improve the answers to the question of, well, what is a hand? Where is the center of the hand? And all of that is vital to answering the question, what is the depth? We are targeting many verticals that have a huge market opportunity for computer vision. Now, there are several growth factors among these that make computer vision relevant. Well, one is just generally improvements in deep learning for computer vision. So there's a classic technique called CNNs. That's a deep learning technique. And it's being supplemented by something called visual transformers. Visual transformers share a common thread with LLMs. They have at their core a very similar principle. And that has enabled computer vision techniques powered by vision transformers to be much more powerful. And there's just untapped. We have this tool, we haven't really used it yet in many spaces. Now, if you can think of LLMs, this creates a little bit of tension with mobile or edge requirements. Many LLMs, they require huge servers and a constant connectivity, and that is not necessarily what we want in many of these spaces. Specifically, for example, around adopting automation within industry, having these expensive models and constant connectivity to some foreign server, that doesn't quite fly. So there are some challenges there, and those challenges produce these opportunities. Now, as we desire to automate real-world processes in the spirit of the promise of LLMs, we need to take computer vision into the real world. And this would apply and enable things like smart vehicles, smart facilities, buildings, and on a larger scale, even smart cities. So there are many layers involved in applying computer vision to the real world. And I've worked on solutions on each of these levels, which I'll bring you through in the next slides. But first off, what are these levels? At the base, we have world mapping. This is just creating a map of a location. Once you have that, the next sort of level is, where am I within the map? And I, in a sense, could be a human. It could be a robot. It could be a car. Anything that moves, really. And together, if you start adding elements, enriching that map, enriching your perception of the world, that leads to reality capture. That is the ability to sort of capture everything in the space and ask questions. And when it comes to capturing everything in the space and asking questions, one important aspect of that is determining the pose and shape of objects within that space. So that's knowing the size, the shape, and where they are relative to the camera or relative to some other point of interest. And then once you make this world dynamic, that's where you start having motion analysis. And that's measuring the changes in the size, location of an object. And all of these things, they require the ability to measure real world distances, lengths, and angles, which is a key part that comes back to the math, geometry, and physics of computer vision. What you see on the screen is some images from a joint venture between the Department of Defense and the Australian Department of Defense. So I was actually in Australia here. And what we have here is a team of robots that their job is to go out and map the world and know where they are within that world. And part of the reason that we were mapping this world was to determine IEDs, improvised explosive device. That's that little red barrel you see here, or other threats, and to explore the space and neutralize them. This sort of technology has also been sort of used in specifically, one of the guys in this images went on to work with the nuclear reactors in Japan after the earthquake for reconnaissance. In the similar vein is localization part of that. So if you have some place that you've seen before and you have a map of, in this example, I think this is the lower level of 30th Street Station in Pennsylvania. Um, we have a wearable system. So someone has a camera on their chest and they're walking around. And the desire is to track where they are just purely visually, largely because there might not be GPS underground or you might not have connectivity. Real time, meaning we're not sending data out to some server and getting the response, it's just too slow, um, from the user's own mobile phone. So that's an example of like edge computing. And this was funded by NSF. So this was an NSF grant. This is an example of visual-based localization. Going deeper, this is an example of robotic manipulation and pose recovery of, these are specifically surfaces revolutions. They're anything that is revolved around an axis that you would make with a lathe, for example. So that's wine glasses, any sort of cups. And this, I think, was in concert with DARPA. So there was a DARPA robot that we eventually had that we wanted it to be able to manipulate and move a whole class of objects. Part of my main work was actually being able to perceive and reconstruct transparent objects. Transparent objects are difficult because they violate a lot of the physics assumptions that we commonly use in computer vision. Most importantly is light goes through them. That's the hardest thing. Light goes through it and gets distorted, which most sensors we have, for example, LiDAR or laser, that's laser radar essentially. The light just passes through and gets scattered. So this is a very hard problem, but it's a very important problem. So this project with the robot on the right was in concert. You see there it has a flask. This is in concert with Merck, the pharmaceutical company. One of their headquarters is slightly outside of Philadelphia, Pennsylvania. And for them, they have lots of experiments they need to run that need constant human attention. And it's constant enough where just to be annoying. So for example, every 3 hours, you might need to rotate something or move something from somewhere to someplace else. And that would mean that long running experiments, that ones that span past the work week, they would either have to pay someone to come in overtime and do nothing for most of the day, or they would have to strategically time everything, and that really ruined their throughput. So this is a good example in the sort of the pharmaceutical space, but also anywhere where there's glass objects. So this is a project that was in concert with Walmart. So, and it's the sort of the mid-level, or the reality capture of a space. So the company's corporate spends all this money to figure out the optimal layout of their shelves, millions and millions of dollars. That's so that your cereal is, right at the eyes of children and things like that. And that's great, but in practice, the stores don't actually implement these strategies. And you have all these problems they call like section drift, which is where you're supposed to have all of your shampoo bottles in this one area, but they slowly move out. You have things not being in the right location, so on and so forth. And so this is one of the patents that I hold, is the system for automatically detecting and segmenting products on shelves. And the bottom visual that you see is very, very cool. The robot is actually, and this is taken by a robot is going across the entire aisle, and we're getting this, I'm stitching together, it's sort of like I'm making like a virtual scanner from this robot. So I'm getting a potentially infinite long image of all the shelving, which we then use to segment. There's a huge desire in many industries to compare what is planned, in this case it's called the planogram from the store, to what is real. We have another instance of this in the construction technology space. So this is, I sort of took this concept over from the incubator in the retail space and applied it to the construction space. So the issue that we're in the retail, it was, can we map the planogram, the file design to reality? And in here, it's can we map a BIM, which stands for Building Information Model. It's your 3D construction document for new constructions. can we map that of the actual construction site? Every day, every 3 hours, depending if we have humans or robots on site. Sometimes we have a human that goes around and captures this, and sometimes we have robots. We take a scan of the entire space and it generates this point cloud, which is in the middle image with associated photos. And we have on the left-hand side, we have the building information model. Every single element is color-coded differently. And the idea is to sort of merge those two and generate something like the third image, which is all of the points that correspond to models that are built or to objects in the model that are built, and knowing exactly where every element is. And what we can do from that is we can do progress, which is the building being built to schedule, but also deviation detection, are elements being built where they're supposed to be built. So that is a much larger scale concept of reality capture. And this was the company of year that we went to Series B and then was acquired by another company called Hexagon, which happens to also make the lasers that are used in the scan. So it was a nice vertical integration play on their part. And then finally, this brings us to Meridian's current main product, which is motion analysis in the context of putting in a golf swing. So we have here is speaking of finding the objects in the scene. That's the lowest level, the bottom rung of those layers. Finding the objects in a scene and tracking how it moves throughout time. So that's both using again physics and the math of what is a club, what is a ball, where is it, how it's moving. And what you're actually seeing in the top trajectory is in the top graph is the trajectory of the ball. And from that, we can get acceleration, we can get velocity. We can also get what's called the stamp of the green, which is a measure of the coefficient of static friction, which is how slippery the grass is, essentially. And on the bottom, we can get some of the real world metrics, which is you can see how far your backswing is, how far you've moved from your center point, and how far you moved in your downswing, and also those angles. So those are key things that you don't get just from your LLM equivalent of AI. You need to go back and apply the math and geometry. That's the beating heart of computer vision. Essentially, I've just presented sort of all of these technological solutions that I've had my hand in. And what I view is each technological solution is like a flexible recipe. And all of them together, we sort of have this nice cookbook of technological solutions. And what we can do with that is we can go out and explore these spaces in industry where there's a potential problems to solve. And we can solve them by adapting one of the recipes from this cookbook. So the first step of this problem validation, and that is teaming up with someone, seeing what problems they have, and comparing it to some prioritizations. And that is there an urgent need for this? Can we monetize it essentially? Is there access to a buyer or user? Is it a clear problem? The technical fit part is, can we adjust our recipes to actually tackle this problem? And importantly, can we scale this? Is it just one little thing, one specific niche that doesn't have much growth opportunity, or actually could we duplicate this many times over? And the next step after that, we've validated that problem with some conversations with people in these spaces, is we find a partner to actually help us bring this into their space. So that's the co-creation step. And we'll develop the MVP with them. We'll do a pilot implementation with them and learn everything that we need to learn. And if that seems successful, we move to the next stage, which is productization. And that's where we'll just iterate, validate the business model, And once that model proves out, that's when we take it to scale.
Camera. Thank you, Cody. That was an excellent walkthrough, really clarifying on some of the breadth and depth of the technology. Cody, I wanted to maybe ask a thing that we've talked about before. I noticed some checkerboards on a lot of those videos, and then kind of figuring out what that real world relation is in whether it's inches or meters or millimeters to pixels. Could you talk about that a little bit?
Okay, so you can see here there's a little, so there's that checkerboard that Josh was talking about, and there's two lines that says ground truth and hypothesis. So the ground truth is how we measure the actual accuracy of something. So in this case, that checkerboard is giving us the ground truth location of the cup, which is essentially saying I placed the cardboard, I measured exactly where the center of that cup is, and I can use that cardboard to sort of cheat and figure out and know where the cup actually is. And then I can ignore the cardboard as part of the technique I'm testing and try to figure out the pose without its help. And then I compare the answers. So that this is a common technique for getting ground truth and also for evaluating how well you're doing. Now, the of course purpose is to come up with a technique that doesn't use that, which is what's also being shown in this video. And the other part of your question is how to turn it back into depth, like how to turn it back into real life measurements. And part of this comes from what's called camera calibration. So one piece of this equation is knowing a little bit about the camera, and that can either be done with like before if it's an object that is issued sent out into the world like your phone's camera. It's actually calibrated at the factory, and its information is saved on the device. If we can't trust that, or if that doesn't exist, there's something called auto calibration, which is a little procedure that runs stealthily in the background that tries to figure out these details just from objects in the world. And with that, we're left in a position where to get scale, we need one of two things. We need either two eyes, and that's how we use to figure out scale and depth, or we need something called a reference object, and that is just any object of known size. In our golfing application, we use the size of the ball. The ball is what allows us to know everything in inches. So we say that the ball is 30 pixels, but we know, or 30 pixels, but we know that that 30 pixels maps to, what is it, 2.8 inches, something like that.
I think
Some const
168, something like that.
Yeah, some constant I've written many times in code. And or for example, like the approximate size of a hand or any other thing that we have, the more accurate we have knowledge representation of a reference size, the more accurately we can establish the scale if we do not have two eyes.
You mentioned that each one of these algorithms is a recipe, and we've got the cookbook. Is there a not to break the analogy, but a situation where we maybe blend multiple recipes together to solve a particularly complex problem?
Oh yeah, definitely. I mean, I think that actually doesn't break the recipe, or you're just I don't know, extending it to I don't know, a buffet. But
A
just
fusion
as though you
meal.
would have many recipes on the table to solve your dinner problem. Yes, many of these technologies may be added together to accomplish a certain end. And I think, I mean, we I sort of showed it as, I don't know, like an onion with layers or something to that effect. And yeah, going back to the top part. And, for certain things, you don't need to go all the way up. We don't need to map the world in order to do motion analysis on golf balls, uh, for example. But, if we were to just extend the golf analogy, actually it might make sense to incorporate where you are in the world into a golfing app if you're on a specific course and need to know stuff about the specific land that you're on. For example, if the ground is sloped, that might be an awesome thing to be able to register in the app because that that affects your swing and all that stuff. So you can
Okay,
imagine applying a technology there and having those two things together.
awesome. Well, Cody, thank you very much for taking the time to talk us through everything you've been doing for the last, over a decade. We're going to see some really exciting things coming forward, but just thank you and thank everyone for joining us.
All right, thank you.